And get started with our next panel. Ralph, sorry.
Well, good morning. Let's go ahead and get started. I'm Ralph McNutt of the Applied Physics Laboratory, a division of Johns Hopkins University. And the panel this panel this morning is going to be on exploring the outer solar system. We have 3 talks, and we're going to try to do about 20 minutes per talk with about 5 minutes for questions, and then that will give us plenty of time to have a panel discussion. I think that this will be, should be an interesting panel. Of course, we've been hearing about how difficult all of this is, although we all tend to make this easy. And of course, getting to the outer planets is an interesting challenge in and of itself. It's not some place that we've been to with very many spacecraft, but we'll find out a little bit from the panelists about some of the issues that are involved. So the first speaker is going to be Torrence Johnson. Let me give you a little bit of background about Torrence, although I think he probably doesn't need that much of an introduction to most of you. Torrence, of course, is a planetary scientist. He got his PhD at Caltech back in 1970 and was the project scientist for the Galileo mission and directed the Galileo science teams through that mission. He's currently involved in ongoing research with the properties of giant planet satellites and is a member of the Cassini science team. And he's also the chief scientist for the Solar System Exploration Directorate at JPL, where he's involved in planning for the next era. So, without more ado, Torrence.
Thanks, Ralph. My title here is an Outer Solar System Exploration and Archetype for the Scientific Method. That's because the organizers told me this was a very academic and serious audience and that I should prepare something suitably lofty. What that really means is I'm going to talk a bit about how we decide what sorts of objectives we undertake in outer solar system exploration and how those are affected by the very long periods of time that it takes to get to the outer solar system, which makes things a little bit more difficult than for some of the terrestrial planets where we have much higher launch rates and cadences. So let me start going back to a couple of the talks yesterday, discuss things like the effect of how science was perceived by the public and by the media and so forth, which could be sort of summed up in many cases as we send a bunch of spacecraft out there and, oh, looky what we found. Scientists amazed, astounded, textbooks rewritten, unexpected results stunned scientists. I can't tell you how many times I've had those types of questions from media. It says, well, aren't you amazed by what you've just found, et cetera? Our friends working on the Higgs boson are in this situation now. Tell me again, sir, you spent billions of euros to find a particle that you were almost absolutely certain was there in the first place, and what are you going to do with it now? In fact, the reality is more complex, but saying scientists confirm their model while finding some new puzzles doesn't make quite as lively copy for the morning paper. And the reality is in between. We do follow the scientific method while trying to develop the objectives and the experiments for our missions. And that was illustrated very nicely yesterday in some of the talks related to the advice that the National Academies and other advisory bodies give to the program here in the US. And there are similar types of roadmaps and so forth done in the other space programs. And it does operate in a more deliberate fashion. This is particularly evident when you look at the way the outer solar system exploration has proceeded. Because of the vast distances and very, very long flight times involved, it means that you have to select experiments sometimes years before launches based on best available scientific evidence, but not necessarily data from the previous mission, which might still be on its way, for instance. And so things have to be designed to be reprogrammable. Mission operations procedures have to be flexible so that they can take advantage of things that get discovered between the time when you made your plans and when you're actually sitting there getting data back from the mission. Now I'm going to illustrate that process not by telling you everything that we've done in outer solar system exploration. You would, even if you're really interested in this topic, you would begin to glaze over after the 60th or 70th slide if I went through that type of procedure. So what I'm going to do is take two specific areas that are somewhat linked and talk about how our objectives for those have changed through the process of a series of outer planet explorations. One is the outer planet atmospheric compositions, and the other is the nature and history of giant planet satellites. These questions are actually linked through the scientific goals because they relate very directly to our understanding of the solar nebula out of which the planets formed, and also our understanding that has progressed over the years as to what the processes forming the planets are. Now I'm going to warn you up front, particularly Ralph, that I'm going to mostly ignore a third major theme that would also be worthy of an entire paper, which is the exploration of the magnetic and plasma environments of these planets. I'm going to touch on that in this particular talk only as it sort of relates to the issue of the interactions of those environments with their satellites, for instance. So you can ask, and when we get to the panel, you can ask Ralph about how you go about investigating the magnetospheres of planets. I'll remind you that at the beginning of the space program, we knew of only one magnetosphere other than the Earth's, which was Jupiter. And it was defined and identified initially through radio astronomy. So that was a major theme in outer planet exploration, running along in parallel with some of the ones that I'm going to talk about. So let me take you back to the beginning of outer planet exploration, which is not quite back 50 years, but almost, and take you back to sort of solar system version 1.0, which is what we started planning the outer planet programs with. It's only 10 years after the Mariner 2 launch that we started thinking about outer solar system exploration because, as was pointed out by several speakers yesterday, we had this wonderful grand alignment of the outer planets that allowed very short trip times for at least a few specific launch dates. And one of my very first NASA briefings was listening to John Naugle tell us about the grand tour in Washington. I was a postdoc at the time. And I thought, getting to Neptune in 1989? Wow, I'll be in an old folks' home by then. And we were all very distressed when that grand idea got descoped, but it was resurrected rather rapidly, as was also discussed by several speakers yesterday. And I'll point out one of the things that didn't get much discussion yesterday was that actually the first part of that resurrection, even before Voyager, was Jim Van Allen pushing very hard on getting a fast, simple spacecraft out to Jupiter to find out what was there with that magnetosphere, and of course to carry Van Allen's Geiger counter with it. And so Pioneers 10 and 11 were very much a part of this kind of restructured idea. They were designed to get out there to Jupiter, find out what was there. Voyager follow along with more of the objectives of the Grand Tour, but go only to Jupiter and Saturn. That was all that was promised, but they would be launched at times which would enable pieces of the old Grand Tour trajectories to be enabled. Okay, let me take you back to our state of knowledge of the solar nebula and the giant planets at that time. We were beginning to get the first quantitative understanding of what the planets were formed out of and how they were formed. And by modern standards, it was quite simplistic, which is one of the things that's changed over this period of time. But Al Cameron put together quantitative pressure, temperature, density models of the solar nebula, and of course he changed it several times per year, so people were always playing pickup with coming along afterwards and trying to figure out how their models matched Al's several months after he published it. And that was coupled with giant planet formation models, which were, again, quantitative, but by modern standards quite simplistic. The idea being that if you got something as big as Jupiter or Saturn, it would hold a hydrogen-helium atmosphere and would not cause major fractionation by Jean's escape from the top of the atmosphere. All of that was true, and so we expected at that time, and this was embedded in the advices from the National Academy, that when we got to an outer planet atmosphere, we would see essentially an unchanged sample of the gas from the solar nebula collected by this massive gravity and preserved for our use for 4 billion years. So hydrogen to helium ratio sort of became the mantra of the people interested in the gas giants at that time, the holy grail, if you will. If we measure the hydrogen and helium ratio in these atmospheres, we will be measuring the original hydrogen-helium gas from which the sun was originally formed. It was believed actually at that point that that would be a better indicator of the original hydrogen-helium ratio than what we actually measure in today's sun, because things going on with solar interior burning and nucleosynthesis and so forth have been changing the hydrogen-helium ratio in the sun. The composition of that original solar nebula also played a role in setting the state of knowledge of the giant planet satellites at that time. We didn't know much about them. It's amazing to think about how little we knew at that time. We didn't really know masses, radiuses, how bright they were, how reflective they were, compositions, ephemerides. General view amongst most of my colleagues in the astronomy and geology world was that we're going to go see cratered mud balls, basically, or ice balls. We did know a few things. This came from my own thesis, actually. I collected all the information we had, some of it from my own data, about the brightness or reflective qualities, the albedo of the satellites, and their density, and all those big boxes and error bars there because we didn't know what their radii were. And we didn't know what their masses were very accurately. So as you can see, you could run anywhere from some of these boxes, like the one for Callisto, J4 as it was called in most of the ephemerides at the time, could run from a density of 1 up to a density of 3. And we had some things that obviously had fairly high density and a bunch of things in between. The Voyager imaging team at that time only had 2 geologists on it, I think, Larry Soderblom and Hal Mazursky. And the planning was based on this type of information. They said, okay, well, we got kind of rocky satellites and icy satellites. We'll go by 1 of each, even though there are 4 out there. And that's what the early planning for Voyager was based on. But data and theory for the outer planet satellites and the systems in general was exploding at this period of time. That same Cameron nebula model that was applied to understanding what the atmospheres of the planets might be like was taken and used by John Lewis to try to make theoretical predictions of what the compositions of the satellite should be like. And he noted that, hey, if you take that solar nebula composition and take that gas down to the temperature and pressure that there is in Al Cameron's nebula, you're going to get satellites that are rather interesting. They'll be about half and half rock and ice. And if they're big enough, like lunar size, radioactive heating is enough to melt that ice. So he said, hey, these aren't just going to be inert ice balls. They could actually be really interesting, evolving planets in their own right. Several other things were occurring at the same time. There was an occultation of a star by Ganymede in 1972. This was one of the only accurate ways to get radii measurements at that time. We'd already measured the radius of Io that way a year or so earlier. That determined the radius accurately. This pioneer early recon of the system at Jupiter allowed the mass of Ganymede to be measured fairly accurately. That was the only one it got very close to. And that density matched Lewis' model almost exactly. It got a density of just about 2, which, when you accounted for pressure effects, gave you a rock to ice ratio of about 50-50. In addition to which, we found out that Io was active somehow or another. There was sodium emission lines, sodium D lines from resonant scattering of sunlight discovered around Io at that time. And the reflection spectra of Ganymede and Callisto were taken, and Europa, and showed that there was water ice on the surface of these bodies. So we had some inkling that the sort of models that Lewis was putting together were correct. And this, mind you, is about the time that instruments were being chosen for Voyager, so think about that. Okay? That's what the Lewis model using the Cameron Nebula looked like. And the basic point here is that at the distance of Jupiter, this is log pressure, log temperature here, and the planetary symbols there show the distance out in the solar system. That's where the water line is, just around Jupiter. You can start condensing water in that nebula and keeping it as ice for over 4 billion years. This was illustrating the occultation of Ganymede. That's myself there on the left in my bell-bottom phase with Bob Carlson with me. We were measuring one chord of that occultation. The other was measured by a colleague of ours in India at the same time, and we got the radius measured very accurately. That's spectra of, in this case, Ganymede and Europa, published by Carl Pilcher. Worked at NASA for many years, still works out with the institute out in Ames, Ridgway and McCord, which showed that those objects were covered with water ice. Okay, now, not long after that, think about this, that, you know, we had the flybys of Jupiter by Pioneers 10 and 11 just a year or two before this. This was a briefing that I gave to the Complex Committee in 1975, pushing for a new Jupiter mission, even though we hadn't even launched Voyager yet. It was based on this theoretical understanding, Lewis's models, that these objects might really be interesting worlds in their own right, and that we needed, despite the fact we knew we were going to get lovely Voyager data, we needed to go back and get detailed study of these objects, and we could do that from a Jupiter orbiter. This is the state of knowledge of the satellites after the Pioneer 10 and 11 flybys, and this now is showing density and radius rather than albedo, but you see two distinct clusters, and on this type of diagram, icy things fall on a line of density and radius down here in the bottom of this chart, and rocky things fall up on the top where the terrestrial planets are. It's interesting to note that this is pretty much the state of knowledge we now have for the best studied exoplanets that we are now beginning to get. We have this type of information. So when we were briefing the public and the reporters at the Cape just before the Voyager 2 launch, this was the sort of cartoon we made up for them of what the satellites would be like. And in many ways, it was really quite sophisticated. We knew that Io was rocky, up in the left. We knew that Ganymede and Callisto contained water, and we suspected they had cores and enough heat to produce oceans. So oceans were already coming into the picture at this time. We didn't know much about Europa. The reason that there aren't any oceans shown on Europa is we didn't know its density well enough to know how thick the ice was. The ice has to be beyond a certain thickness for it to be able to actually melt and produce an ocean under it. So that was a question mark at that time. So we had modified the Voyager plans a bit based on all of this understanding and theoretical discussion. We couldn't reselect the instruments at this point, but we did add a couple more satellite scientists, and we increased the flybys due to some very fine trajectory work by Jeff Briggs, also worked at NASA headquarters for a long time, who found out that you could, because of the resonant orbits, get several satellite flybys with each Voyager pass. So Voyager planning and science was modified to do that. So you all know the result of that. This is a not scientifically correct photo montage showing the Voyager family portrait of all 4 of the Galilean satellites. And just to remind you, we found cratered Callisto, Ganymede, cratered areas, but areas that also look geologically active. Europa, very, very puzzling. Very few craters, clearly indicating some form of resurfacing. And the ocean models versus we have a thin ice crust on top of a warm mud models were the 2 types of models that came out of Voyager at that point. Io's volcanism. Active volcanism, a big plume rising over the limb on the right side there, shooting up 100 kilometers or more, shooting dust and sulfur dioxide gas and condensed sulfur dioxide out 100 kilometers or more. So, at that point, we were still planning the Galileo mission. That was 1979 when we were there. The Galileo mission had actually gotten its start in 1978. And we took the Voyager data then and said, okay, well, what can we do based on the Voyager data to change our Galileo plans? In 1976, over a year before Voyager launched, our science assessment group, which was headed by Jim Van Allen, made recommendations to headquarters. An AO was put out, and that's contained in the AO materials and followed the directions and priorities for complex reports of that era. Key elements in that was hydrogen and helium was still king. We needed to get that information, although the theoreticians were already beginning to mumble things about, well, the helium might condense out and fall toward the core, and it might not be quite as simple as we thought. And in addition to that, there was an increased emphasis on satellites and interaction with the magnetospheres because of all this activity we saw around Io and other places. So they went up to the top of the priority. This was that report in August of 1976 that went into the AO for the Galileo mission. And preparing for that and trying to respond to Voyager, as I said, the Voyager 1 and 2 flyby produced a number of surprises. I will point out that the active volcanism wasn't really a surprise. There was a paper earlier that year by Peel et al., Stan Peel et al., that said, oh, tidal heating ought to be able to produce volcanism on Io. The surprise to a scientist was much more subtle, was that everybody should have known that tidal heating was capable of happening on the satellites, except for the fact that if you looked in the ephemeris books, they all showed the eccentricity of the satellites was 0. Can't get tidal heating with 0 eccentricity. But the dynamicists knew that the average eccentricity was 0, but with all of this interaction between the gravity of the satellites, the instantaneous eccentricity was not 0, and you could get tidal heating. So tidal heating came strongly to the fore at this point in terms of satellite possibilities. And we modified the mission plan to increase the number of satellite encounters for Galileo from 3 to 12. NASA only wanted 3 because they wanted to keep the cost down, and we also stuck Europa into the equation. Okay. Several things were happening simultaneously at this point, okay? We were planning Galileo. Voyager was now flying by Saturn. And for the purposes of this story, the major important thing that Voyager found at Saturn is what it didn't see. It didn't see the surface of Titan, but it did establish that it had a huge, thick hydrocarbon-rich atmosphere, and it didn't see a lot of craters on Enceladus. little tiny Enceladus, only half the size of Vesta, and it looks like it's been resurfaced. So that type of thinking went into Cassini, and we started planning for Cassini jointly with ESA 3 years after Voyager encounter with Saturn and 5 years before the Galileo launch. Originally, it was planned as sort of a super Galileo with probes for both Saturn and Titan. Too expensive, it was de-scoped. At that point, Titan got the nod, partially because of the cooperation with our European colleagues, who in the studies were going to build the probe. Very interested in Titan. There were problems in doing a deep enough probe at Saturn, and so Titan got the nod, and Enceladus went to the top of the list. Again, on the theme of scientists surprised and astounded, it was no surprise that we saw stuff going on at Enceladus. The reason we saw stuff going on in Enceladus with Cassini was because it was on the top of our target list for very good reasons. That's where we were with the science assessment study for Cassini. Galileo launch, Jupiter arrival. As I said, to try to go over all of Galileo's discoveries would take 2 or 3 more days of seminar. Probe went in, big surprise. The atmosphere was not solar composition, and I won't go into the details of this, but basically it's enriched in both condensable heavy elements and in the noble gases, indicating that the makeup of that atmosphere is more complicated than just capturing a big piece of the solar nebula. More complicated, and the delivery of those noble gases is particularly problematic because it implies that those gases must have been delivered by way of being trapped in very cold ice, colder than one would expect from solar nebula models at Jupiter's distance. So there's some complexity going on there. Those results are factored into the types of objectives we now have for Juno, and also led to the decadal survey recommending that we do a Saturn probe to complement this information. Okay. This is going to be a fast slideshow because my moderator is giving me a 2-minute mark. Ganymede's got its own magnetic field, things we found. Io's got high temperature silicate volcanism, stuff going on all the time. Magma generation on Io is by unit mass rate 1,000 times that of the Earth. Europa, which you'll hear a lot more from a subsequent speaker, we found ice flow surfaces clearly resurfaced, things moved around on the surface, looking very much like melted terrain. I used to have one here with the Titanic for scale, but magnetic signatures of oceans. If I'd told the complex committees years earlier that we're going to take a magnetometer to Jupiter to discover oceans, they would probably have thrown me out of the room. So it's fortunate that we took the magnetometer anyway for other good reasons. Basically, the magnetic field is deflected around and these satellites as if they were acting like global electrically conducting spheres. And gee, what can be electrically conducting? Not ice, rock, or ionospheres. At that level, salty seawater is just right. So we now have a more sophisticated view of where water might be in the solar system, and you'll hear more about that from Bob Pappalardo. So I'm going to end this up with coming to the Cassini, and you'll hear more of that from my colleague, Professor Russo. We did put a probe into Titan's surface, and the Mars guys screwed us up and put a picture of one of their, no, that's actually Titan's surface. But also looks like it's been fluid worn. And in this case, the fluid is probably liquid hydrocarbons, almost certainly liquid hydrocarbons. And we got a view of those from sort of an airplane window point of view on the way down with the Huygens probe, showing valley networks. And we landed in something that was not like this, but was a little moist. This is a ethane lake in the northern areas, which was discovered by the radar. This is a radar image colorized for radar reflectivity. And you'll see more of that too, I suspect. We also have specular reflection from the infrared off those lakes, because we took several instruments that could see through the clouds. And then Enceladus. Enceladus plumes, I said it wasn't surprising we saw something at Enceladus because we knew it was an interesting place. But I must admit that these pictures of plumes on Enceladus, heat flow from that southern polar region, plumes on the Terminator, planetary heat flow implied by those plumes is that the heat flow in those cracks that are producing the plumes may be 10 times what you see in geyser fields in Yellowstone. So, amazed, surprised, astounded? Well, yes, actually. Thank you.
And out of time, but we have about 5 minutes for questions. Torrence, don't run away yet. So, questions for Torrence. Don't be shy. Oh,
Greg's not shy.
that's not, I know that's not a problem. Yes, please.
Thank you for that wonderful talk. My name is Mangala Sharma. I'm an astronomer with the Department of State. I have a question for how you went from 2 scientists on the Galileo, on the Voyager team first to several hundreds of scientists who work with you at JPL now and who are on all of these missions.
Well, let me be just I was really speaking of scientists. We started out with Voyager having a science team that had about, for the imaging team, now this is the imaging team, had about 10 or 12 scientists on it. But they were mostly people who were interested in the atmosphere of Jupiter. Because the satellites weren't believed to be too interesting at that time, we only had a couple of geologists. NASA then re-looked at the team and the objectives as the mission progressed and added some more scientists to the team. And then most of the scientists on the team had their own postdocs and graduate students. And then there were other teams that were dealing with the magnetosphere and so forth. So now, then you add in the international cooperation aspect of it. We had many French spectroscopists on that team. And when we got to Cassini, as you will hear, there was a massive collaboration with ESA so that we have perhaps 400 scientists actively engaged with about 50-50 split between the US and Europe on that.
And so the scientists are also working as project managers for their own instruments. And
usually they have an instrument manager, but they're so-called PIs. You have PIs of each of the instruments. Each of these missions had approximately 11 instruments on it. And I was speaking mostly about the imaging team when I was talking about the number of scientists we had. But even there, that was an expansion, and each of the other teams also underwent an expansion like that.
Greg.
So I'm amazed I haven't thought to ask you this question before in all the years that I've known you, Torrence.
I haven't thought to answer it either.
Yeah, well, now we're going to put you on the spot. So, I mean, you portrayed this rigorous approach to following the scientific method, which it really is a nice example of that paradigm. Of all of the surprises that you guys did find, and you personally, what actually surprised you the most? What was the most amazing thing that you did not expect to see at Jupiter with Galileo?
At Jupiter with Galileo. So I was going to come up with Titan. I did not expect to see a terrain on Titan that looked so Earth-like. It was eerie when we came down there, and it's apparently because the hydrological cycle, even at near liquid nitrogen temperatures, using liquid hydrocarbons, produces the same physics and the same sorts of things. At Jupiter, I would have to say that the most of the things we found were things that we went looking for. You'll find Margie Kivelson in her part of that Van Allen report said we're going to be looking for magnetic fields at the satellites. That is not a huge surprise. Getting the induction signatures of the oceans, I think, was the biggest major factor. That wasn't something we could count on, and it was a surprise to find that all three of the icy satellites seemed to have a strong signature of liquid water.
Yeah, Torrence, we talked a little bit earlier, just in conversation about, and then you mentioned it just now, that the state of knowledge of planets in our own solar system back in the 70s is sort of the state of knowledge we have now about exoplanets today. And we'll touch on this later in the panel discussion in the afternoon. But where do you see the line between the planetary program and the more astrophysical exoplanet program, and what do you see as the ways to make sure we're not stovepipe between those two programs for what is really a very common set of goals?
That's a very good question. I'm hoping your panel will, and you will address some of that. It's very obvious from our perspective, you and me as scientists looking at this, that once you are not just counting these things, but actually putting them on mass radius diagrams, you are doing planetology. And the community is beating a path in that direction as we speak. How NASA is going to be able to respond within their system to that, with their different pieces of the traditional disciplines at NASA, is a challenge. And I hope Jim Green may have a chance to speak to that.
Let's get one more quick question.
Yeah, I was going to ask, pretty much the question was just asked, but then that got me to then going out a little further in the solar system, beyond Pluto. I know Pluto has got its 2015 mission. Do you predict within the next years that we'll go out to some of those larger bodies beyond Pluto?
If they could put my thing on, I can show you one slide that shows the answer to that.
Okay. Put Torrance's talk back up.
Excuse me?
AV people.
Yes. No, sorry. Johnson, yeah. Thank you. And the last slide. Yeah, you always leave a slide at the end.
The real last
Yeah,
slide.
the real last slide. That's fine. Okay. And blow that up. Okay, this is what we're doing now. And that's the New Horizons on the way out. This is a timeline. The green bars are the time it took to plan the mission. The red bars are how long it took to fly it. And the symbols inside the red bars are planetary encounters. We've had continuous data coming back from the outer solar system for 40 years. Okay, we have Juno on the way out. Get to Jupiter. You notice that everything is, and then there's nothing after Juno, New Horizons, and the end of the extended mission for Cassini. There'll be an inevitable gap of a decade or more before we get a satellite back after this 2015 is going to be great. It's going to be really great. We're going to have lots of stuff going on. But beyond that, there's not much in the pipeline, and even if we reverse that tomorrow, there would be an inevitable gap. So we're back to one of these things like occurred in the 80s that we saw referred to yesterday.
Let's thank Torrence again. So the next talk is going to be given by Arturo Russo on Europe's rendezvous with Titan, the European Space Agency's contribution to the Cassini-Huygens mission to the Saturnian system. And just by way of introduction, let me mention that Arturo is a former professor of history of physics at the University of Palermo, Italy, and his research is in the history of 20th century physics. He's published on quantum physics, the science-industry relationship in Italy and the U.S. between the two world wars, cosmic ray physics, particle physics at CERN, and the history of space research and telecommunications in Europe. And I think that this is probably going to be a very interesting talk. As Torrence was mentioning, of course, Cassini was an international mission, and I think that's something that tends to get overlooked a lot on this side of the pond, more so than it should. And yet, if I remember correctly, and perhaps I'll get corrected, but I believe that the seeds of what turned into Cassini-Huygens actually were originally planted in Europe with Daniel Gautier and Wing Wen Ip about 1982, if memory serves me correctly. So, and last but not least, if it hadn't been for the fact that it was an international mission, we probably wouldn't have flown it. But anyway, so let's welcome our next speaker and a little bit about Huygens.
Thank you, and I'm very happy to be here, but let me apologize for my English now. But if you don't like it, I can shift to my good Italian. The Cassini-Huygens mission to Saturn and its satellite system is the most ambitious effort in planetary exploration ever mounted. It was launched in October 1997, and the mission was realized as a joint endeavor of NASA, the European Space Agency, ESA, and the Italian Space Agency, ASI. It consists of a spacecraft performing multiple orbital tours around Saturn and a probe released from the main spacecraft to parachute through atmosphere to the surface of Saturn's largest and most intriguing satellite, that is Titan. NASA provided the orbiter, ESA provided the probe, and ASI provided the high-gain antenna and other hardware system for the orbiter. The scientific instruments were realized by scientific teams in the US and in ESA's member states. As you know, both the orbiter and the probe have successfully accomplished their scientific missions. The Huygens probe completed its mission on the very day of its descent through Titan's atmosphere on 14 January 2005, while the nominal mission of the Cassini orbiter came to the end on 30 June 2008, 4 years after the spacecraft entered orbit around Saturn. NASA, however, has approved 2 extensions of the mission that is now due to go through the September 2017. In this presentation, I will briefly discuss 3 aspects of the history of Cassini-Huygens as seen from a European perspective. The first is the institutional framework which set the stage for the establishment of an important European effort in planetary exploration. During more than 2 decades, in fact, the European space science community felt that for technical and financial reasons, Europe could not compete with important programs in the United States and in the Soviet Union in this field. It was only in the mid-1980s that an ambitious European planetary mission was considered as a realistic possibility following the successful Giotto mission to Comet Halley. So Huygens was the first European mission devoted to planetary exploration. The second aspect is the decision-making process which led to the selection of the Huygens mission by ESA. The decision to adopt a scientific mission in ESA's program is the outcome of a highly competitive process involving the various national and disciplinary sectors of the space science community, the ESA executive staff, the European space industry, the space policies in ESA's member states, the relations with NASA and other potential international partners, and so on. Finally, the NASA-ESA relationship is the third focus of my analysis. While scientific cooperation worked smoothly and resulted in the successful achievement of the mission's objectives, it was not so easy to cope with the different political and institutional frameworks in which the 2 agencies were operating. The difference in the budget procedures is particularly important in this context. Decision-making can be very long for ESA, but once a project has been selected, its financial allocation is also approved. So, provided no cost escalation occurs, the project becomes legally binding for member states, and there is no threat of cancellation. NASA, on the contrary, is a national agency whose overall program and budget has to be negotiated annually with the federal government and the Congress. Funds can always be shifted from one program to another on the basis of political considerations, congressional lobbying, or national security priorities. The idea, oh no, sorry. What is it? A page. The programmatic framework for the selection of the Huygens mission is the so-called Horizon 2000 long-term plan for space science, approved in 1985 by the space ministers of ESA member states. The basic philosophy of Horizon 2000 was the establishment of two classes of projects. The first included four predefined cornerstones, that is, ambitious and technological challenging missions to be realized over a 20-year period of time. The second class included a number of standard missions to be selected through a competitive selection procedure. Within the framework of Horizon 2000, planetary science finally received a proper role in the European space effort. One of the cornerstones, in fact, was devoted to an ambitious project for a comet sample return mission. This eventually became the Rosetta mission, launched in 2004. Moreover, planetary mission proposals could be now submitted for competitive selection in the standard mission program. And the ESA director at that time, Director of Science, Roger Bonnet, wanted to foster planetary missions in the selection process for the new standard mission. But why Titan? Well, this has some way anticipated by the previous speaker. The idea of a mission to Saturn and its satellite system can be traced back to the early 1980s on the wave of the successful Voyager missions. One of the most important discoveries of Voyager 1 was the intriguing composition of the atmosphere of Saturn's largest moon. Not only was it confirmed that molecular nitrogen was the main constituent of the atmosphere of Titan, which with a few percent of methane, but the infrared spectrometer on Voyager showed that many organic molecules were also present. The surface of Titan was completely obscured from the Voyager camera by a thick orange-brown smoke made of a mixture of various hydrocarbon and nitrogen compounds. To the eyes of the Voyager scientists, Daniel Gauthier and others, this planet-like satellite resembled what our Earth should have looked like some 4 billion years ago, before organic life started to colonize its surface and produce oxygen by green plant photosynthesis. The fundamental difference between the early Earth and Titan is the low temperature of the latter's surface, which makes it impossible, the presence of liquid water, and then the emergence of life. On the contrary, the intense organic chemistry at work in the primitive Earth did have a chance to evolve into prebiotic chemistry and eventually into biology. Subsequent erosion, plate tectonics, and the evolution of life itself have obliterated all records of those original conditions and processes on our blue planet. Titan now could provide the Earth's human inhabitants of today with an opportunity to travel back in time if they were able to travel in space up to there. So, as it has been told, in July 1982, a group of 29 European scientists submitted to ESA proposals for a Saturn-Titan mission to be realized in the framework of Horizon 2000. The project Cassini, as they named it, called for a Saturn orbiter carrying a probe to be parachuted through the atmosphere of Titan. The interest was in the atmosphere of Titan, mainly in the atmosphere. The project was to be realized by an ESA-NASA collaboration, with Europe providing the orbiter and NASA the Titan probe. 18 scientific institutions from several ESA member states were represented in the group, whose membership included representatives of 4 disciplines: atmospheric science, planetology, magnetospheric physics, and exobiology. The underlying idea was to study the whole of the Saturnian system, including specific objectives for each of its elements: the planet and its ring, the magnetosphere, the icy satellite, and Titan. This concept of system science was an important element in fostering a large support behind the Cassini project within the European space science community and promoting the mission through ESA's highly competitive selection process. The European initiative had a counterpart on the other side of the Atlantic. The project for a Saturn orbiter and Titan probe mission was among those recommended in 1983 by the Solar System Exploration Committee, the SEC, of the NASA Advisory Council. It has been mentioned yesterday, so I will not go back to this theme. But I want to mention that these initiatives received an important institutional support by the Space Science Committee of the European Science Foundation and the Space Science Board of the American National Research Council. In April 1982, these two organizations established a joint working group to define the framework for an ESA-NASA cooperation in planetary exploration. The joint working group eventually recommended that 3 missions should be carried out as cooperative projects by the turn of the century. Listed in order of the launch sequence, these were a Saturn orbiter, a Titan probe, a multiple asteroid orbit, and a Mars surface rover. This represents also the priority in planetary exploration as seen at that particular moment. So, you have already seen that. An assessment study of the Cassini project was conducted in Europe between April 1984 and June 1985 by a team of 13 scientists, 9 from the US and 4 from Europe. Reversing here the idea of the original proposal, the Titan probe was soon identified as ESA's contribution to the mission, while NASA would provide the main spacecraft based on the Mariner Mark II spacecraft. The Titan probe, for its part, was considered within the technical capability of the European space industry, and the estimated costs were within the budget allocated to a standard mission of Horizon 2000. The Challenger accident in January 1986 forced the dramatic redefinition of NASA's planning, but the Mariner Mark II program was eventually confirmed, but with a 2-year delay that deferred the start of the Cassini project until 1991. On this basis, ESA decided to support an industrial feasibility study of the Titan probe to be built in Europe. Again, a group of American scientists and engineers collaborated in this feasibility study. The study report was published in September 1988. 1 month later, the ESA decision-making bodies were called to select the first mission in Horizon 2000. So, on October 25, 1988, the European space science community at large convened in the beautiful medieval city of Bruges in Belgium to discuss 5 mission proposals submitted to ESA for the selection of the next scientific mission. The European Titan probe in the cooperative ESA-NASA Cassini mission was one of them. 3 other mission proposals addressed the ultraviolet astronomy, radio astronomy, and gamma-ray astronomy, respectively. The last one, called VESTA, was a cooperative endeavor of ESA, the French Space Agency, CNES, and the Soviet Space Research Institute, IKI. It aimed at visiting a number of asteroids and comets by 2 spacecraft with release module and penetrators. As usual, in the ESA selection procedure, after the public discussion within the scientific community, the agency's scientific advisory bodies were called to issue their recommendation about which of the proposed missions should be selected by the agency's Science Policy Committee, on top blue, composed of the national delegations of ESA member states. This, in fact, was a 2-step procedure. First, the Astronomy Working Group and the Solar System Working Group would issue a recommendation in their respective fields of interest. Second, the Space Science Advisory Committee the SAC would make the final recommendation to the ESA Director of Science and the SPC. So, for the Solar System Working Group, the choice was between Cassini and Vesta. A very difficult choice indeed, as both missions were dedicated to planetary exploration and considered excellent and scientifically highly interesting. The decision, of course, was a matter of politics as well as of science. From the scientific point of view, a close-up study of a number of asteroids and comets was as interesting and exciting as parachuting a probe onto a planetary body in the outer solar system. The Vesta mission promised to pursue and extend the small body exploration program that ESA had begun with the Giotto flyby of Comet Halley. Cassini, for its part, would lead Europe to the frontiers of solar system exploration, and the European industry would acquire unique know-how in the domain of atmospheric re-entry probes. The two missions, however, were very different as regards their political support, scientific constituency, and international framework. Cassini has been conceived from the very beginning as an ESA-NASA collaborative project in which ESA visibility would be secured by the fact that Titan probe would be built in Europe and its mission operated by the European Space Operations Center in Darmstadt, Germany. There was a large and variegated scientific constituency in Europe and in the United States, and the American colleagues were eagerly awaiting for the decision by ESA because they wanted to use this selection in support of their own lobbying activity for the Cassini approval in the US. In support of Vesta, there was the powerful lobby of the French space agency, the CNES. The French space policymakers insisted that Vesta would provide the European space science community with the opportunity to establish a cooperative venture with the Soviet Union, thus restoring a measure of balance in international cooperation after the difficulties experienced in the past, Ulysses, Halley mission, and so on. So the discussion was very lively and impassionate, and finally a formal vote was called by which the Solar System Working Group recommended Cassini as the candidate project in the field of solar system. It was now up to the SAC to make the final choice between Cassini and the candidate project recommended by the Astronomy Working Group, that is the Gamma Ray Astronomy Mission, GRASP. The discussion within the 7 membership of the committee covered all aspects of the important decision to be taken. On the one hand, the supporters of the Gamma Ray mission claimed a well-established European tradition of scientific excellency in high-energy astrophysics. On the other hand, the Cassini advocates stressed the importance of opening a new fascinating territory to European space science. Moreover, by paying the ticket for the Titan probe, ESA would provide European planetary scientists with access to the NASA-built Saturn orbiter. In the event, the advocate of Cassini succeeded in convincing the majority of the SAC members to support the Saturn-Titan mission, which was thus formally recommended by the representatives of the European space science community as ESA's next scientific project. The ESA Science Policy Committee finally endorsed the SAC recommendation, and it decided that the probe should have its own name, and this was the Cassini-Huygens, who was the discoverer of Titan. Huygens thus entered the ESA scientific program as Europe's first planetary mission and the first mission in the Horizon 2000 long-term program. What about the US? It took 1 year, but eventually the Congress approved in October 1989 the Mariner Mark II program, which included both Cassini and the cometary mission CRAF. NASA and ESA then issued parallel announcement of opportunity for instrument proposals on the Saturn orbiter and the Titan probe, respectively. Following peer review on both sides of the Atlantic, the two space agencies approved the scientific payloads and interdisciplinary investigation. Finally, a memorandum of understanding was signed by NASA and ESA on the Cassini-Huygens mission, and so the mission was well on its way towards its scheduled launch in November 1995. The way, however, proved to be fraught with difficulties arising less from technical problems than from political uncertainty in the United States. In October 1991, the US Congress dwarfed the 13% increase for the NASA budget requested by the White House, approving only a 3% increase, hard enough to compensate for inflation. As a consequence, NASA decided to delay the launch of the Saturn mission until October 1997. All this could hardly be accepted in Europe. A 2-year delay would cost ESA an additional $30 million, the ESA Director General wrote to the NASA administrator. Such unilateral decision is not in the spirit of the Memorandum of Understanding, he concluded. No less irritation was expressed by the European space science community. You see here a quotation in a letter of Saturn to his counterpart in the United States. And here you have an excerpt of comments in the Science Policy Committee, the Swiss delegate, the Dutch delegate, the chair of the SAC. But despite all efforts, it was hardly possible for ESA and the European scientists to influence the US Congress debates on such an important item in the federal budget. So in autumn 1989, the Congress had approved the Kraft-Cassini program within a budget limit of $1.6 billion. And the cost of Cassini was now, Cassini alone, was estimated at about $1.7 billion. So one of the missions had to be cancelled, and eventually NASA decided to cancel the Kraft mission and undertake a significant reconfiguration of the Cassini project in order to reduce its cost. That was not the end of the story. A new budgetary crisis burst in 1994, and in this situation, either Cassini or the gamma-ray AXAF mission that eventually became Chandra had to be cancelled by NASA, and the prospects for Cassini were not encouraging, as the mission did not enjoy the support from NASA administrators, Daniel Goldin. Cassini, in fact, was the perfect antithesis of Goldin's faster, cheaper, and better policy. A mammoth mission conceived 10 years earlier, which would not provide scientific results until more than 10 years later. Its cost was to be measured in billions of dollars, and a failure at launch or beyond would have been devastating. Moreover, its management suffered from the complexity of a large international cooperation and an 18-instrument payload coming from countless scientific institutions in 2 continents. So he did not hide his distrust toward Cassini, and apparently he was prepared to cancel it. Let's skip this one. The reactions, again, were very strong in Europe. Here you see a letter. This is an unprecedented initiative taken by the ESA Director General, Jean-Marie Luton, who wrote to the US Vice President Al Gore, and you can read the quotation here. And a strong diplomatic action was taken by ESA member states governments whose ambassadors in Washington appealed to the State Department to warn about the devastating consequences of the eventual cancellation of the Cassini mission. In the event, President Bill Clinton came to NASA's aid by redirecting other spending in order to shore up the agency's science budget, but Golding, the NASA administrator, demanded that the whole Cassini program, including the Huygens probe and the antenna under development in Italy, should be submitted to an independent review by a team of external scientists. This again was felt in Europe as an unacceptable violation of the cooperative spirit. But after some tense meeting, the review was eventually accepted. Finally, following the review, the Cassini-Huygens development program went on smoothly. The mission was successfully launched on 15 October 1997, and after a 7-year cruise, Cassini entered orbit around Saturn on 1st July 2004. 6 months later, on Christmas Day, as you can see, Huygens was released by the mother spacecraft and started its 20 days and 4 million kilometer cruise towards Titan. On Friday, 14 January 2005, a group of nervous and excited scientists gathered in the control room of the European Space Operations Center in Darmstadt, Germany, to attend this epochal event in the history of planetary exploration and enjoy, hopefully, the crowning achievement of their scientific life. For the first time since the beginning of the space age, a human artifact would be landed on another world in the outer solar system. The scientists and their distinguished guests, including ministers, space agency officials, and journalists, were waiting. Around noon, the news arrived that a faint radio signal from the probe had been picked up by the Green Bank radio telescope in West Virginia. Huygens then had survived the entry phase and was alive. Late in the afternoon, the first scientific data relayed by the Cassini spacecraft arrived at ESOC. Scientists hurried to analyze, and soon the press got the first stunning images of Titan's surface. A long week of intense work and celebrations was about to start. Well, everyone has his own flag.
Excellent. Let's take time for a couple of questions. As you're up.
Wes Huntress, thanks very much, Arturo. It's too bad we couldn't get another talk just like yours from the U.S. side, because I assure you that the drama associated with getting a new start for Cassini and also preventing its cancellation is also filled with a great deal of drama on the U.S. side, and particularly inside the halls of NASA itself. Just a comment. I was the pre-project study scientist for Cassini, and I was also the associate administrator at NASA who had to deal with the potential cancellation of Cassini. And every morning, I went into my office, and I printed my resignation letter, dated it, stuck it in my pocket, and went upstairs and talked it out to Mr. Golan. So there were a couple of necessary steps we had to go through to convince Mr. Golan not to cancel Cassini. And so the Congress came to our rescue, the administration came to our rescue, the scientists came to our rescue, and Europe, thank you very much, came to our rescue.
You saved both Cassini and Aksaf. You saved both Cassini and Aksaf, and Chandra.
Next question.
Hi, Peter Markowski. I'm struck by the parallels of the international cooperation aspect of this with the ISPM earlier in the 1980s, kind of the political battles and then the European protests. When ESA was planning and deciding on Cassini in the 80s, were there explicit concerns both from the scientific community and from ESA planners that sort of foreshadowing that something like ISPM will happen again? And I mean, did they make that explicit?
Maybe you have read the quotation of the members in the Science Policy Committee. Once, we cannot go again through the same story, and then we're referring to the ISPM experience. Mm-hmm. So, but in this case, there was a different situation, in fact, because first of all, there was a strong constituency behind Cassini in the United States, probably much stronger than it was in the case of a ISPM, I guess so. And secondly, there was a new balance of powers between the two agencies.
Mm-hmm. Thank you.
One final quick question.
Thank you, Arturo. This is really fabulous work. So I have a question about the previous interinstitutional relationships that are going into the decision about Cassini from the European side. So you mentioned it was going up against a mission that was involving the French and the Russians, who of course had a long history of cooperation already by that point through the 1970s, right? And I'm wondering to what extent there was a... You can't hear? Try this way. So you mentioned that moment in Bruges when they were making the decision to have Cassini or to have one of 4 other missions. And one of them, you said, was a Russian and French collaboration. Yes, Vesta. So of course the Russians and the French had already been collaborating for many years through the 1970s, right? So that was an existing cooperative arrangement. But I'm wondering if there was, first of all, institutional precedents for the relationship between Europe and America, or if this was a new collaboration that had really been formed through individual relationships on Voyager. If this was Europe attempting to make some bridges with the United States in a way that they hadn't before, and what would lead them to make the political decision to work with the United States as opposed to support another Russian and French collaboration. So I just want to know a little bit more about that moment of decision making.
That is a long story, but anyway, the French had a long tradition of collaboration with the Soviet Union, and ESA had a long tradition of cooperation with NASA.
Okay.
So as far as I know, there was no institutionalized collaboration between Europe and the Soviet Union, but there were personal contacts and individual forms of cooperation. In the case of Vesta, there is another aspect, that the mission was conceived and early developed by CNES and IKI. So ESA joined at a later stage, and within the ESA staff there was not that much interest in getting involved in this mission, because they felt they should be considered as something like a junior partner vis-a-vis the French and the Russians.
Of course. Thank you.
Thank you, Professor Russo, again. Thank you. So our final talk this morning is going to be by Robert Pappalardo on revealing Europa's ocean. And let me just say that Bob is a senior research scientist in the planetary science section of the science division of the Jet Propulsion Laboratory in Pasadena, California. That's the other PL, the one on the West Coast. His research focuses on processes that have shaped the icy satellites of the outer solar system, especially Europa, and the role of its probable subsurface ocean. He's the Europa study scientist for the development of future Europa mission concepts and a member of the NRC's Space Studies Board. So, Bob.
Good morning. As other speakers have already mentioned, the evidence for a subsurface ocean at Europa is potentially profound. Europa has a surface like no other in the solar system, and its subsurface arguably offers the greatest likelihood for life beyond the Earth in our solar system. Let's take you back to 400 years ago, when, of course, Galileo's observations of the Galilean satellites, including Europa, helped change our sense of place in the cosmos. There was another center of motion out there, which argued for Copernicus's idea. And Galileo, observing over subsequent nights, saw all 4 Galilean satellites revolving about Jupiter, and using the JPL Solar Sisters simulator, we can reconstruct which ones he saw. And on that first night, it looks as though Io and Europa were grouped together into apparently one little star. The first spacecraft image of Europa was brought to us by the imaging photopolarimeter on the Pioneer 10 spacecraft. It's the only image of Europa from the Pioneer 10 or 11 spacecraft, principally a magnetometer mission. As Torrence reviewed, we knew a little bit about Europa and the other satellites from telescopic observations. We knew that the surface composition included water ice based on spectra. We had some idea of the density, though that information was improved by Pioneer, showing that Europa had a density of about 3, rocky but less than Io, a little bit different from Io. Here's another fun exercise. You can take the new JPL Eyes on the Solar System tool, ride along with the Pioneer spacecraft, and at the right time, on the right date of December 3rd, 1973, look toward Europa and zoom in and see the view that we had at 200 kilometers per pixel at the time of Europa's surface. And it seems just like, or analogous to Galileo, who famously recorded Neptune without knowing it in January 1613. Pioneer also spotted Neptune next to Europa. Through the 70s, as Torrence alluded to, there was the thought that there might be oceans in some of the large satellites of the solar system. And it was John Lewis and his student Guy Consolmagno and then Fraser Finelli who proposed from models of composition and radioactive decay that there might be oceans within these satellites. And then in the late 70s and early 80s, tidal heating was discussed as a potential way to maintain oceans. Though Cassin and Peel and Reynolds wrote that convection might kick in and freeze an ocean. That is, if an ice shell is thick enough, then the ice might convect in a solid state like a lava lamp, and that, they thought, would freeze up an ocean. So oceans came and went through this period, and actually it was Steve Squires in a paper with Cassin, Peel, and Reynolds who said, well, you know, there might be enough tidal heat if we push the parameters a bit to maintain an ocean within Europa underneath a thin enough shell that it won't convect. And that ocean could be there still today. And that was followed up by Huygens and Stevenson, who used a more sophisticated model in 1989 to say that, yes, it looked like there could be sufficient heat to maintain an ocean beneath a conductive ice shell using a more sophisticated model of tidal heating. So that set the stage, so that earlier work set the stage for Voyager, which saw few large impact craters on the surface, which suggested a very young surface. Or perhaps the larger craters were relaxing away, as Mike Malin pointed out in the early 80s along the terminator, along the right-hand edge of that Voyager 2 image at the right. There is mottled terrain, pits and domes along the terminator. Are those tiny craters? And in fact, is the surface very old? The bright lineated planes suggested crustal mobility. It was Schenck and Seyfert back in 1980 who looked at the Voyager images and said, you know, there are dark bands that could fit back together with the bright pieces moving back into place like puzzle pieces. But it was nearly a decade before Schenck's then controversial idea of crustal mobility was published. Right around the time Huygens and Stevenson said, you know, it's possible to maintain an ocean. So Voyager 1, of course, had relatively poor resolution at Europa, 20 kilometers per pixel, still 10 times better than Pioneer did, and Voyager 2 had 10 times better than that, 2 kilometers per pixel, but it would remain for Galileo to really greatly increase our knowledge of Europa through imaging and through other techniques. There were, as Torrence alluded to, 12 prime mission close approach flybys by satellites by Galileo, and 3 were usable close Europa flybys. And then there was the Galileo Europa mission, because Europa was turning out to be so exciting that an extended mission would focus on Europa, with 8 close approach flybys of Europa, excuse me, though one of those was gravity only, and 2 of them ended in radiation-induced upsets of the spacecraft. So really with 5 close approach, additional close approach flybys, we were able to learn amazing things about Europa. Of course, it is about the people. I had the pleasure to work with this motley crew as an affiliate of the Galileo imaging team. Mike Belton in front, you can recognize. Let's see, Torrence, you have your hat today, but there he is on the right. Clark Chapman in front, Rick Greenberg in the back right, Ron Greeley in the back, organizing the crew a bit, Jim Head in the back left. We've been having fun on Facebook, so now I found this photo tagging away. The first images from Galileo of Europa were only slightly better in geometric resolution than Voyager 2 images. They were 1.6 kilometers per pixel, but the much better camera, a solid-state imager, was able to get much higher quality images. And here the surface shown in false color as compiled by Paul Geisler at the time. And what we saw is the right-hand side is littered with some of these pits that we were getting a feel from Voyager. And both Clark Chapman and I looked at the size distributions of these pits and said, you know, they're all kind of the same size. They're all turning out to be several to 10, a little less than 10 kilometers across, which suggested maybe they're not impact craters, maybe they're endogenic features related to internal activity. There were these spots littering the surface, the dark spots, and they also seem to be about the same size. Maybe they're somehow related. Is it related to some sort of internal volcanism or other activity? We found that the surface was brightening with age. Older features were brighter. The idea of non-synchronous rotation had come up from Voyager days, and based on this color composite, Paul Geisler argued for non-synchronous rotation. When we looked at the age of lineaments, there seems to be a rotation of lineaments through time as well, consistent with the icy shell moving independent from the interior, slightly faster than interior, as if lubricated, decoupled from the interior by a subsurface ocean. There were a series of papers published based on some of the first images arguing for crustal mobility, non-synchronous rotation. And this picture from the same sequence was on the cover of the New York Times arguing for crustal mobility. So Schenck and McKinnon, it seemed, were right. The puzzle pieces were fitting back together. This is Europa's surface as it looks stretched out into a global map as we know it today. Very few impact craters. There's one here, this bright one, Pwyll, or Pwch if you're Welsh. There are only about a dozen or so that one can recognize, and from observations of impactors in the Jovian system, we know one should hit every 3 or 4 million years. So you do the calculation, it comes up that Europa's average surface age is about 60 million years. Europa has been repaved since dinosaurs roamed the Earth. We don't know whether that was in a spurt 50 or 60 million years ago, or if it's a continuous process and is ongoing today. But why would Europa die out just 50 or 60 million years ago? In fact, it's probably either an ongoing process or Europa may go through cyclical activity. Predictions of tidal heating as tied to Io suggest that Io is pulling Europa back and forth and increasing its eccentricity and decreasing it again on a time scale of 10 to the 6th years or so. Here's what those ridged plains look like close up. Those lineaments are ridges, not just single ridges, but double ridges crisscrossing the surface. It looks like generations of ridge upon ridge, or sets of ridges, have created those ridged plains. And then there's that model terrain where those pits and spots are. Some show chaotic terrain. Looks a little like hamburger, and that ridged plains has just crumbled in place to form that chaotic terrain. Now, I'm a geologist, and so we were working to understand whether the surface geology told us about an ocean, but it was the magnetometer team. If anyone has discovered an ocean, it was them who, through measurement of an induced magnetic field at Europa, found strong evidence that Europa is acting as a conductor, that Jupiter's external field is inducing a magnetic field in Europa, and that remains the strongest evidence for subsurface ocean at Europa today, that still exists today. And of course, the gravity data, through measurement of the inference of the moment of inertia, tells us that Europa is almost certainly differentiated with an iron core, a rocky mantle, and then an H2O layer, something like 100 kilometers thick. Here's a little illustration from Michael Carroll of Europa in Jupiter's immense magnetosphere, and an illustration of that induced magnetic field at Europa. Recall that Europa is bathed in high energy plasma charged particles with kilo electron volt and mega electron volt energies are slamming into Europa at all times. And while that is a nasty environment and would kill a person in 15 or 20 minutes if exposed to it, it is potentially life nurturing, because when high energy particles slam into H2O, they make H and they make O. And some of those things recombine, and they recombine with the other contaminants on the surface. And they make things like peroxides and formaldehyde and O2. Europa doesn't have much of an atmosphere, a picobar, 10 to the minus 12 bars, but it does have essentially an atmosphere frozen into its surface. There's O2 at that surface. If all of Europa's oxidants could be dumped into its suspected subsurface ocean, then that ocean would be more oxygenated than is Earth's ocean. And that could serve as a fuel for life. We need to understand the processes of whether that material from the surface gets into the ocean and how. Here's what the surface looks like a bit closer up. Sorry, no scale bar here, but again, these spots are something like 7 kilometers across, and ridges are commonly a couple to 5 kilometers across. Some of them are quite bizarre, seeming to bounce across the surface in a cycloidal pattern, not something you're used to seeing on a planetary body. Okay, I'm getting the signal to speed it up a bit. The story of Europa's ridges is interesting because there are many ridge models that have been proposed, and while they're the most ubiquitous feature on the surface, they're the most controversial as well. Is the surface, the ice shell being cut completely through and tidal flexing, opening and closing ridges, a model that has been supported by Rick Greenberg and colleagues? Or are there other models that might involve solid state ice, and it's almost incidental that the ocean is below, enabling large scale tidal flexing? And one model illustrated is the idea of shear heating, that back and forth motion created by tidal flexing is what is heating a plane in the subsurface and warming that ice and pushing the surface up to form a ridge. And interesting in the sense of the story of Galileo and Europa exploration, these models somewhat led to a schism of, is Europa's ice shell thin or is Europa's ice shell thick? Torrence likes to call it the pizza debate. Is it thin crust or thick crust? And we were working some of the ridge ideas, and Rick Greenberg pointed out that was developing this model, and I pointed out that, well, this model couldn't work if the ice shell, because the ice shell had to be less than about 7 kilometers thick to cut all the way through, and the tidal heating models were suggesting a thicker ice shell, and his response was then the ice shell must be thin. And so he ran with that rather than questioning the model itself. Whereas in a thicker shell model, the ice shell can be pierced down to a ductile layer and pulled apart atop warm, flowing glacial ice. And that's the model illustrated at the bottom right for bands on Europa. We were able to zoom in on some of these wedge-shaped bands that Schenck and McKinnon had originally investigated. And again, the puzzle pieces of each side fit back together perfectly, and the center is striated, analogous to what we see at the mid-ocean ridges at spreading centers on the Earth. And then in the thin debate, it was, is that atop warm ice or is that atop liquid water? Impact craters, as Zibby Turtle and Betsy Pratso argued, like Puil, argue for an ice shell that's relatively thick, at least 8 kilometers thick, or you wouldn't get a nice crater morphology. And later, Paul Schenck wrote on these multi-ring structures. There are only 2. And he invoked a model that had been developed for Ganymede and Callisto that says if we penetrate through the ice shell to a fluid layer, then the crater fills in, this large crater essentially fills in very rapidly, pulling the brittle ice along inward with it to form these concentric rings. And based on the scale, about 40 kilometers across for the inferred crater, he said, well, then they've penetrated to liquid water at about 20 kilometers depth. Consistent with the tidal heating models. In terms of surface composition, there's a question of what this dark reddish stuff is that we see, and based on infrared spectra, the leading candidates are sulfate salts or sulfuric acid hydrate. And in reality, it's probably a combination of those two. So is Europa's ocean like Epsom salt or battery acid? The answer is more likely that it's like Epsom salt, but that the battery acid is created at the surface by irradiation of the surface. Here are some of those freckles, lenticulae is the Latin for them, that when we saw them first rang a bell with me as what I had heard about that Reynolds and Casson model way back when, that convection may have kicked in the ice shell, and perhaps what we're seeing is the tops of diapirs, warm ice blobs that have risen up through Europa's ice shell, again implying that it would be more than 20 or so kilometers thick. And the bottom is showing a model by Amy Barr of that warm flowing ice, all the red being only about 30 Celsius below zero in terms of the temperature. Warm ice, even though the surface is 100 Kelvin, that warm convexing ice would be 240 or so Kelvin. An illustration of the lava lamp-like model of Europa's subsurface convection. Some of the most fascinating terrain, our chair's starting to get up. Some of the most fascinating terrain is this chaotic terrain. And in the thinner thick model, the issue was, has Europa's ice shell melted out completely, or have blobs of warm ice risen and moved to the blocks above, like in a mosh pit? And recently, Brittany Schmidt has suggested an interesting hybrid model, that chaos may form above a melt zone in a thick ice shell, that essentially we're looking at areas that used to have lakes beneath them the size of one of the U.S. Great Lakes, and that some of these regions may still have lakes beneath them today. And so the discussion continues as to whether we're actually looking at floating icebergs. And here, just for you, Torrence, the Titanic is about 270 meters from stem to stern. So Europa may have the ingredients for life. In terms of water, more than 2 times all of the Earth's oceans, in terms of the essential elements from its formation and from impacts bringing carbon and other elements. It may have chemical energy from above, oxidants created at the surface by irradiation, and potentially energy from below. If the mantle is warm, if it is tidally heated, then there could be black smoker-like activity pouring reductants into the base of the ocean. And it's probably a relatively stable environment, somewhat variable, but simmering for 4 billion years. So that leads to basic questions about the ocean, its existence, its extent, its salinity, about the ice shell, the existence and nature of water within and beneath, the nature of the surface ice-ocean exchange, composition, the distribution and chemistry of key compounds, the links to ocean composition, and the geology. What are the characteristics, formation of surface features, including sites of recent or current activity? And these all relate to that overarching theme of Europa's potential habitability. The history of trying to develop the next mission to explore Europa from the late 1990s could be a talk in itself, but I'll simply say that the latest iteration is a very feasible one that could cost about $2 billion, short of launch vehicle, would address these ocean ice shell composition geology objectives, and could have a reconnaissance camera as well to set the stage for a future lander. It would do several dozen close flybys of Europa to understand the nature of its ocean and understand its habitability, potential habitability. And just to finish, there are important fundamental questions remaining to answer in our solar system, especially with regard to its potential for life beyond Earth, its origins and its commonness. It was 400 years ago Galileo's observations of the Galilean satellites changed the human perspective on our place in the universe, and it's fascinating to think that one of those worlds could in the future change it again. Thank you very much.
Thank you, Bob. It's tough to explore and talk about an entire world in 20 minutes. I'll tell you what, why don't we go ahead and assemble the panel, and so let you take a seat, Torrence and Arturo, if you can come on up. And if you have a question for Bob, why don't you try to get first in line? Okay. But we will see. Please go ahead.
Okay. I don't see speaker. Oh.
It's hard to see around the columns.
You mentioned about some kind of the variations in the mutual position of the, say, Europa and Io, you know, and in addition to the regular change. So are these deviations mostly just produced by the Laplace resonance, I mean within Laplace resonance, or it's some kind of additional mechanism exist? And how deep such fluctuations are, whether their influence on the depth of the ocean or only on the temperature?
Yeah. So the idea that's been developed is that by Io heating up, it could heat to the extent that its ability to dissipate heat actually decreases. And to conserve angular momentum, that will actually end up changing slightly its orbital eccentricity. And it will drag Europa along as it does so. And recent models have suggested Europa's ice shell thickness could fluctuate from something like 10 or 15 kilometers up to something like 30 kilometers. So it's possible Europa may have even experienced a thin shell-like history and a thick shell-like history, and that may vary on something like a 10 to the 6 year cycle. About 10 to the 6 years is in the models, but the models can be tuned. There are a lot of parameters, so.
Yes.
Thank you. John Sarkisian from CSIRO Australia. This is a question for Torrence. We've heard about how the spacecraft get to the planets and we're able to image them and so on, but very little's been said about how that information is actually returned.
Torrence, would you like to say a few words about the Deep Space Network involvement in those outer planet missions?
Sure. Communications is obviously a critical element in all of these things, and it often operates beneath everybody's visibility level. It's just something that happens. As a scientist, I just regard that as part of the magic, because I can't figure out how we get all those bits back from out there. And I know, John, that I talked with you the other day walking over, and then I realized reading your bio that you were one of the people who were at the Parks facility in Australia that helped bail us out when our communications system became a little flaky on Galileo. And it's a marvelous story in itself, how these communication systems, codes, cooperation amongst the various institutions and radio tracking facilities around the world go. You're quite right to bring that up.
Heidi.
This is for Torrence. We'll hear from Chaz tomorrow how most about the exoplanets, and the Kepler spacecraft is showing that many thousands of candidates are Uranus and Neptune-sized bodies, and yet the only mission that has ever gone to an ice giant was launched before I even graduated from high school, and now I got gray hair. And you've already pointed out that we're looking at a radio dark outer solar system now. What's your thoughts from a historical perspective of how that got lost from the Jupiter orbiter and the Cassini-Saturn orbiter, and why did it get lost that we don't have an outer planet orbiter? What happened, and what's the lesson learned so we can fix it?
I think the discussions yesterday illustrated how cyclical the funding for this entire enterprise is, not just outer planet exploration. It's not something that's taken for granted at the political level. It's something that we have to continually make the arguments for. I would just remark from a historical point of view, we were well served by jumping on top of the Grand Tour alignment. I mean, that for the outer planet exploration, because that actually got us some data in remarkably short times. And it's not going to happen again for a while unless we get warp drive. So I think we have not lost the drive to do these things, but we're still struggling with the generational nature of how long it takes to do them. I agree with you there.
Thanks, Jennifer Tessie, Princeton University. That was a great question. Of course, it's interesting to note that the generational moment corresponds to when a lot of attention has been placed on Mars, as opposed to how long it takes for satellites to get to the outer system. I was really struck by the presentations, which look like we're talking about planets and moons and institutions, but we're also really talking about some important relationships that made those systems work. And I'm struck by the number of times we've seen, that Torrence has participated in several generations of missions, or Paul Schenk's name coming up over and over again, or these strong relationships between NASA and ESA that enabled something like Cassini-Huygens to be the success that it is. And I think I, like many people in this room, have been very dismayed or distressed at the cancellations of some of the larger scale international collaborations between NASA and ESA, specifically whether it's ExoMars or the potential of a joint mission to Jupiter's moons. And I'm wondering if the three of you could speak from your experience as to what are the parameters for success for building the kinds of strong relationships, whether it's across institutions or across missions or across continents, that enable these kinds of missions to go forward.
Let me just make a preliminary comment on that and then ask my colleagues, is that I have frequently tried to make the point when speaking to media that we got the wrong name on our program by allowing it to be called unmanned or robotic. It is profoundly human, and the crew of these spacecraft are right here on Earth and in the command center. And now with social media and other things, we can bring the rest of the population of the world together with that. That's been an evolving picture. And that's true in the science community, but there's a broader context to it.
In planning these next missions and looking toward future missions. There was a meeting several years ago working with many of the same members of the science definition team been working with for many years, when came to the realization it's about the journey, that we have to be enjoying ourselves along the way and working with good people who have that very long-term vision. And I think those who are dedicated to that future exploration work so well together because they have that long-term common goal. And so I'll stop there.
I have not much to add to what I said, but I think, first of all, you have to consider that space science is not a scientific discipline. It's a complex, a set of very different scientific disciplines, and so there are always competition and cooperation aspects which play a role in this field. Secondly, even given the scientific disciplines that we call space science is not only science. They need technological means, rockets, spacecraft, communication networks, political decisions, huge amounts of money. So it's not only science, and science is not even the most important driving force behind space science. Third, the most challenging and important scientific mission in space have to be done in collaboration. Big collaborations, small collaborations. Just having a launcher is a collaboration. Having the deep space network for ESA is essential. If you want to go to the outer solar system, you need an RTG generation. You cannot have this in Europe. So that demands, in any case, some kind of collaboration. And all of this implies scientific personal relationships, but also complex political and economical negotiations. So the situation is always very fluid. The difference in the budget system in Europe and in NASA has been the major stumbling blocks in several cases, and was a source of not less important controversies in some cases.
Yeah, I would note further that Professor Russo pointed out the tensions in the relationships between ESA and NASA particularly. What amazed me was that the relationships survived. I wasn't certain when we started talking on Cassini whether my European colleagues would even talk to us after what the United States had done with respect to the Ulysses program. And it was personal relationships that allowed people to say, hey, you know, there's a bigger picture here. We have to work together on this. We're not going to be able to accomplish these things.
So let's take one final question.
Let me pick up on that theme, actually, because that's my question, and ask the striking difference between what Professor Russo described and what Bob has recently experienced in the construction of an international program for outer planet exploration. It seems now, as a result, we're in a phase where U.S. and Europe are going apart and planning their programs independently, not just the outer planets, but at Mars too, it seems, as we heard earlier. What's the impact of the current situation on this with respect to the future outer planet exploration?
I'll start with the Europa Ganymede discussion, and maybe others can pick up. But we've certainly, so we were working together as one wonderful group when the U.S. said, okay, we're not doing Europa, and Europe said, well, we are doing this Ganymede mission, which has become JUICE. Again, the personal relationships continue. We certainly want to work together with our colleagues in Europe to explore the Jupiter system. There will be U.S. participation in the JUICE mission. And we're doing all we can on our side to try to keep alive that vision and resurrect a Europa mission for the exploration of Europa and the Jupiter system, including Ganymede, as a whole. But without the U.S. participation, we will continue to have tantalizing hints of what Europa is like, but we won't have answers. And my fear is that 50 years from now, when we do explore Europa and we get a lander to the surface and we sample that stuff, my fear is we'll say, why didn't we do this 50 years ago? Because it could be that important.
All right, let's thank our panel once more. And you may blame the moderator for cutting out 7 minutes of your lunch.
No, quite the contrary. Thank you, Ralph. You did a fine job, and thanks to the panel for such a stimulating discussion. A couple of quick announcements before we break. If you haven't already done so, please take the opportunity to avail yourself of the oral history recording crew. They're not down at this end today. They're down at this end. When you go out, it'll be to your left. We've got a lot of experience and talent in this room, and let's share that as much as we can with the public and with the next generation. We will be reconvening at 1 o'clock, so keep an eye on the clock. 7 minutes won't hurt us, but we do need to be back at 1. And lastly, please remember the admonition to take a buddy to lunch. Again, the advantage of having us all here physically in one place is the interpersonal interaction, and lunchtime's a great time for that. So without further ado, see you back at 1.